Hello again, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinar units possible. And today's topic is acoustic fatigue. And this is just going to be a very basic introduction to acoustic fatigue, so you might call this Acoustic Fatigue 101. And before we actually get into the fatigue part, though, we're going to have to discuss some of the basic concepts of acoustic waves. So sound waves propagate longitudinally. So on the left you can see a speaker, and it's driving some air molecules towards the human ear there. And where those little particles are joined together, those become the peak pressure zones, and then in between those peak pressure zones there's a spraying apart of those molecules. So sound waves propagate longitudinally, and sound waves can propagate through air or through water or even through the earth. And when the sound waves are propagating through the earth, the seismologists would refer to those as P waves or primary waves. And of course longitudinal waves can also propagate through metal structure like beams and plates and rods as well. So it's common, even though these are longitudinal waves, to represent the time histories as a sinusoidal function there. So you can see the peaks of the sinusoidal pressure correspond to the regions where the molecules are compressed together, and where the molecules are spread apart, that becomes the valleys of the sine function. So that's just a very basic introduction to acoustic waves, and we'll probably have a later webinar where we go into more details about wave behavior. So here's a formula that we're going to be using today, and this is the formula for the overall sound pressure level. So OA SPL. And the formula for this is, well, we would take the RMS, the root mean square pressure, then we would divide that by a reference value, and then this is a base 10 logarithm here. So take the base 10 logarithm of that ratio, multiply 20, and that's going to be the decibel level. So this is an important formula for today's unit. Now this reference value, there are two different reference values that we're going to discuss here. The most typical one is 20 micropascals RMS, and that would be for air. So the sound is propagating through air. But on the other hand, if sound is propagating through water, which conducts sounds much more efficiently than does air due to the increased density, the reference is going to be 1 micropascal. And I'm not sure whether we're ever going to cover underwater acoustics in this webinar unit. Maybe we will someday. So the common one that you need to know for now is this this reference value for air. Now today, instead of using pascals, we're actually going to be using English units. So we're going to have our pressure in terms of PSI. So the equivalent reference value for air in terms of English units is approximately 2.9 times 10 to the minus 9 PSI RMS. So if you ever want to do this as a hand calculation or write your own program to do that, and you want to use English units, then you could use that reference value as an alternative. But pretty much any time you see an overall sound pressure level on a plot, that plot will include, or at least should include, what the reference value is. Now, this first formula here, this is for the overall sound pressure level. So imagine we have broadband acoustic excitation. That would be the overall sound pressure level. Then what we can also do is divide the sound into 1/3 octave bands. The sound pressure spectrum into 1/3 octave bands, I should say. So we can also take the sound pressure level for an individual band. So this formula is really the same formula that you saw before Only in this case, instead of this being an overall sound pressure level, instead it's the sound pressure level within a given frequency band. And each frequency band will have a center frequency f sub c. So that's the argument you see there, and then also here as well. So let's talk about these 1/3 octave bands that we're going to be using. These are proportional bandwidths where the bandwidth increases with frequency. So the higher up we go in frequency for that center frequency, the greater the bandwidth will be. And each band will have 3 frequency parameters. The lower frequency limit will be FL, FC is the center frequency, and FU is the upper frequency limit. So those are the 3 frequency parameters that describe each band. And these bands are going to be taken as consecutive bands that are non-overlapping. So here's just a couple of formulas here to get more acclimated to the frequency band calculations. So if we take our upper frequency, our band limit, and the lower band limit frequency f sub L, multiply those together, take the square root, that will be the center frequency of that band. So you might have been thinking, oh, the center frequency is just simply the midpoint between the upper and lower frequency. Well, more properly, it's the square root of that product. Then the upper frequency is equal to 2 raised to the power of 1/3 times the lower frequency limit. So what we have here is we have 3 different frequencies, and we've got two formulas. So if we know any one of the frequencies, and we know that it's a 1/3 octave band, then we can calculate the other 2 frequencies. Now, we're also going to take a look, okay, let's also take a look, what are the respective center frequencies of 2 adjacent bands? So if we take the band center frequency of band I, multiply by 2 to the power 1/3, then that will equal the center frequency of the next band to the right. So this is band I plus 1. And just sort of as a quick note, the way we're actually going to apply these is going to be not with exact numerical precision. These are just sort of some approximations for what we're actually going to do, and I'll explain that. So here's a table of 4 possible 1/3 octave bands, and let's go ahead and just look at the 3rd column over. This is the band center frequency. Now we've sort of gotten in the habit within the industry to make these center frequencies just neat and tidy numbers. So you can see these are whole numbers here. There's nothing, there's no decimal point appended to those numbers. So in order to make these center frequencies neat and tidy, we're sort of just taking some kind of approximations of all these formulas I just showed on this slide. And the way this also will work, again with approximation, is, okay, here's band 1. We're defining the center frequency at 100 Hertz. Then the lower frequency for this band will be 89 Hertz. The upper frequency will be 112 Hertz. So then as we go to the next band, which is the 2nd row, this upper frequency, 112, becomes the lower frequency for the next band. And then you can see that pattern continue as we step up in 1/3 octave increments. So you can see how those upper frequencies then become the lower frequencies for the next band. And okay, here's another thing to notice. What is the width of each band? Well, if we take 112 minus 89, then that would be 23 Hertz. That would be the bandwidth for band 1. Now the second band here, if we go from 140 down to 112, that would be 28 Hertz bandwidth. Then you can see a 40 Hertz bandwidth and a 44 Hertz bandwidth. So actually I probably should have just added a column to to put those bandwidth numbers in. But you can see as we go upward in frequency, the width of these bands increases. So just please keep that in mind. And this is called a proportional bandwidth. So we're going to go ahead and have some fun here. And what we're going to do is we're going to generate a white noise pressure time history. It'll be 60 seconds long, standard deviation 1 psi, sample rate 20,000 hertz with no band limiting. And the reason we're going to do this is we're going to generate this pressure time history, and then for the first time ever in this webinar unit, we are going to take a sound pressure level of data. In this case, it's synthesized data. And this will help prepare us and get us ready for doing our acoustic fatigue. So let's go to our vibration data GUI here, and let's see what version we're up to this week. So if I go to vibration data, this is our GUI package here. So this is version 6.6 this week. So let's generate a signal. It's going to be a white noise signal. It'll be 60 seconds long, standard deviation of 1. Sample rate 20,000 hertz. No low pass filtering this time. Let's go ahead and calculate this white noise time history. So far this is a review exercise. So we get the nice bell-shaped curve for our histogram. It's characteristic of white noise. We have our actual white noise time history, and our amplitude is going to be psi. That's the more proper amplitude for what we are doing today. Park that off to the side. Let's call this white underscore noise. So we're going to save this time history to our MATLAB workspace. So it's white underscore noise. Then that's saved. So what are we going to do with that next? Well, that's going to be our pressure time history, our sound pressure time history. And maybe I'll make a few other remarks about this. So this is really pressure psi along the y-axis. And you see this value 0 here, the 0 baseline. This is actually referenced to the ambient pressure. So typically at sea level, normal day, the air pressure would be 14.7 psi. So this oscillation would be occurring about the nominal 14.7 psi for the ambient environment. So you might think of this as being the gauge pressure rather than the absolute pressure. So let's go to time history input. It will be a pressure, and it's going to be a sound pressure level. Click on that. So for the first time we're doing a sound pressure level calculation. This script calculates the sound pressure level of a time history. The input array must have 2 columns, time in seconds and pressure. And I just noticed that little typo there. That should be an L, not an I. So I'll go back and fix this, and by the time you download the software, this will probably be hopefully version 1.1 won't have that typo. But nevertheless, let's go ahead and type in white underscore noise. This is the time history we just synthesized. It's in PSI. Now weighting networks, probably for just about everything we do in the webinar series, we will not apply a weighting network because we're dealing in the physics and engineering realms. If we were doing like human hearing, we're concerned about how is the sound going to affect a human, then we might use a scale or maybe one of these other scales as well. But these other scales are more for human hearing. The human ears are very nonlinear in terms of their frequency response, and for that reason these other scales have been derived. And maybe in some future webinar we'll cover those, but not today. Let's take our look at our viewing options here. Okay, when we do this, our time history reappears, and in this case it does have the proper y-axis label, which is pressure in PSI. And again, this is our white noise time history as a standard deviation of 1 psi RMS. Okay, let's see. Now, this choice here, what we want to do for our options is to kind of have a fairly low delta F. And we're not going to concern ourselves with statistical degrees of freedom, because what we're going to do is we're going to do a constant delta F processing just as an intermediate step. But once we get the levels in terms of these constant bandwidths, we're then going to assemble or group those levels, using a some of them root mean square type approach into the 1/3 octave bands. So let's just do row 11 here. That'll give us a delta F of 1.22 hertz, and that should work well enough for what we're trying to do today. Let's go ahead and calculate the sound pressure level. So we're doing this for the first time in this webinar series. And the plots, actually we're on my right monitor here. So here we have our 1/3 octave sound pressure level. The overall sound pressure level is 170.7 decibels, which is very high. We'll talk more about that later. The reference value, so we're very careful when we do these sorts of plots to mention or to explicitly state what our reference value is. So I have 20 micropascals there. And another interesting thing about this reference number is if our overall pressure were actually to be 20 micropascals, then the resulting dB level would be 0. But anyways, along the y-axis here, we have our sound pressure level in terms of decibels with our reference value duly stated. And these frequencies here are along the x-axis. They're really center frequencies for the 1/3 octave bands. And the more honest and proper way to represent a 1/3 octave SPL is to use a bar chart. And that's really the way we should be plotting this data. But it is so common and so conventional to connect the dots via straight line segments that's what I've shown here. And as I'm thinking through that, I probably had ought to go and put in an option here for plotting in bar chart, or maybe I'll just make that an additional plot output so that the users can have the data both ways. And I think I'm going to assign myself an action item to do that. So maybe by the time you actually download the software, instead of this being version 1.0, it'll be version 1.1 with the typo corrected and a bar chart output as a supplement. Okay. So we've done that. Do we need to save this SPL? Let's see what we have on our PowerPoint slides here. So here was the PowerPoint version of the time history. And then we did a sound pressure level. So these slides are just reminders here. And as always, I'd like you to do this for homework exercises. And then we took our sound pressure level. And here's another thing to note. I should have mentioned this already. This is white noise. So if we were representing this white noise in a power spectral density format, you would see that the level would be a flat. It would be a horizontal line. But we're grouping the energy into 1/3 octave bands. So the bandwidth is increasing as we go up in frequency. And the net result of all that is for white noise, the sound pressure level increases by 3 dB per octave. And an easy way to think of the 3 dB octave increase is that if we go up a decade in decibels, so in other words, if we go up plus 10 dB and our frequency is also increasing by 1 decade, then that corresponding slope is 3 dB per octave. Now previously we had also looked at pink noise, and if we were to synthesize a pink noise time history, take its sound pressure level, then the pink noise would have a flat sound pressure level at some constant dB level. And maybe you can do that as a homework exercise. Okay, so let's see what else. So now I'm going to be honest with you. What we did today was just a little bit contrived. And in a future webinar, we're going to study high-intensity acoustics. Because what really happens here is that the higher up we get in acoustic level, the more skewed our data becomes. And the reason for that is our negative pressure can never drop below minus 14.7 psi. And I've got a saying. It actually comes from a philosopher named Baruch Spinoza. And he said, nature abhorreth a vacuum. So the air does not like to go towards a vacuum state, so we get sort of a nonlinear effect as we go up in higher decibel levels where the pressure becomes positively skewed. And today we're not demonstrating that effect, but just sort of put that thought in the back of your minds, and maybe in one of the upcoming webinars we will take a look at high-intensity acoustics where we see that skewness effect occurring. Okay, here's just some typical dB levels. These are just typical ones. So let's say we have a large rocket. So maybe it could be a static fire test. Maybe it could be a liftoff event. And if we were to have a microphone nearby, then the decibel level could be anywhere from 180 to 194 decibels. And that would be for a large rocket. And these are the overall sound pressure levels. And then you can see the other decibels levels as well. And we might revisit this chart later on if we do a webinar unit on human hearing. Okay, so now we're actually going to get into acoustic fatigue. So we've just sort of covered some basic concepts on acoustic waves and decibel levels, and we found how we could take a sound pressure level. So now we're going to use our frequency domain methods to assess acoustic fatigue damage for a given sound pressure and a given plate or small panel. And when I say frequency domain methods, do you remember, hopefully you remember in previous webinars, we went over the Derlick method and some other methods for doing fatigue damage and rainflow cycle type calculations within the frequency domain. Now for this case, we're going to have a rectangular plate, and it's going to be subjected to a uniform acoustic pressure field. So this is going to be a very simplified example. In many cases, acoustic pressure fields are more complex. There could be spatial variation from one point to another. There can be variation in phase angle and coherence and correlation and all those different things. And those are more advanced acoustic topics, and we will probably get to those in some future webinar. But today we're just going to start out very simple, where we have a uniform, fully correlated acoustic pressure field. So that means all the phase angles are the same, acting with a normal distribution against a plate. And this plate will have dimensions of 18 by 16 by 1/16 of an inch, or 0.063 inches. The material will be aluminum 6061 T6. We're going to assume that it's simply supported on all four edges. We're also going to assume 3% damping for all the modes. And 3% damping for all the modes means that the Q value is going to be 16.67. And another thing I should mention, although I don't have this on the bullets here, is that this plate is we're going to assume that this is a baffled plate. So there's no flanking noise there. So in other words, we're going to assume that on one side of the plate we have this acoustic environment striking the plate, and on the other on the back side of the plate, it's just an ambient pressure environment. So in fact, while we're all together, I'm just going to put in a baffled plate. Okay, so let's go onward here. So we have our plate dimensions, material properties, boundary conditions, and we've even specified what the damping is going to be. But to do this fatigue problem, we also need to know what the acoustic pressure field is going to be. So what is our acoustic pressure field? We need one. So we're going to take some data from a Boeing 737 aircraft. Now the companies like Boeing and other companies that manufacture these aircraft, they have just, who knows how many gigabytes or terabytes of acoustic pressure data for these aircraft during the various flight phases and for various Mach numbers and altitude and engine configurations, all that. And they have that in their data vaults, and it's all proprietary data that they do not share. But there is a NASA document that does have some data where some external fuselage acoustic pressure measurements were made for a 737 aircraft. And we're just going to use these as sample data for our example today. So we're going to subject our plate to the Boeing 737. And there's two locations we can choose from, the aft fuselage or forward fuselage. And this is for the external skin. And we're going to assume a Mach of 0.78. So that would be a typical cruise velocity. And so we're going to take a sound pressure level corresponding to the measured data from the NASA document. We're going to assume that the pressure is uniformly distributed across the plate, both in amplitude and phase. And let's see. So we're going to take a look at the corresponding pressure spectral density. This will be a pressure power spectral density. We're also going to assume that at the center of the plate we have a stress concentration factor of 3. So, who knows, maybe there's a hole with a bolt in it or something, but one way or another, for some reason or another, there is a stress concentration factor of 3 at the center of the plate. So that's some conservatism there. And in this case, we're going to determine the time until failure occurs at the nominal level. So the nominal level would correspond to the Mach 0.78 case. And also at 6 dB increments. And I should also say this is going to be for 25,000 feet. So there is a NASA reference publication shown here. This is in the public domain. It can be you can do a Google search on that and download that from an internet site. And let's go ahead to this program here. This is what I've actually done is I've introduced this as a library function in the vibration data GUI package. So let's go import data to MATLAB. And let's go to aircraft external fuselage pressure, PSD in flight. So this is a PSD library function. What I've done with this reference data from the NASA document is, well, first of all, there's a family of curves in this document for different altitudes and Mach numbers. But we might want some different altitude or different Mach number. So I've done some aerodynamic scaling methods based on the dynamic pressure and Mach number so that we can enter in whatever reasonable altitude we want and whatever reasonable Mach number we want, and it will do the scaling, extrapolated scaling from these curves for our given case. So for our plate, we're going to subject it to the aft fuselage location. It will be English units here. And we're going to say we're at 25,000 feet. And our Mach number is 0.78. And we need an output array, so I'm just going to call this the, the sound pressure level. Now let's call it the aft. It's actually going to be a PSD format. Let's call this aft PSD. We'll actually take a look at both the PSD and the sound pressure level. Okay, so I get two curves, one of which you can immediately see. The other is parked off to my right monitor, so let me make this a more user-friendly size there. Okay, on the left we have our 1/3 octave sound pressure level. It has an overall level of 135 decibels, reference to 20 micropascals. So we have sound pressure level dB versus center frequency in hertz. Then we have a corresponding pressure PSD. And this corresponding pressure PSD has an overall level of 0.0113 psi RMS. And then I've noted the Mach number and altitude. The y-axis is pressure psi squared per hertz. And then we have frequency in hertz. Now those two curves look different. And the reason they look different is that this is a 1/3 octave presentation here. And in this case, our power spectral density is based on a constant delta F spacing. Of course, there's also a difference in our amplitude format. In this case, we have a density calculation, or the y-axis parameter is a density parameter, whereas the y-axis here is simply the overall energy within each band. So those are some of the differences, the two differences between this pair of curves here. But they do represent the same data, and our go-forward plan here is to use the pressure PSD. So that's why I've saved the pressure PSD as aft_PSD. So that's now in our MATLAB workspace. So you can see that kind of off to the right there. We have aft_PSD. So the next thing we're going to do is apply that PSD to our plate. So let's go to vibroacoustic, acoustics and vibroacoustics. We have to step through a series of dialogues. So we've got vibration data _acoustics _vibroacoustics. It seems a little bit redundant there, a little bit wordy. Let's go to vibroacoustics. And for our vibroacoustics option, we have a rectangular plate subjected to a uniform acoustic pressure field. And again, I need to go in and do a little change here and put that a baffled rectangular plate. So here we have plate vibroacoustics. Nope, that's not where I wanted to go. Got to click on the third item down. Okay, so here we have vibration data _rectangular _plate _uniform _pressure. That's also a bit too wordy. Plate bending mode response to an applied uniform acoustic pressure. And I need to put in the adjective baffled there. So maybe by the time you download this software, that adjective will be in place, and this will be 1.2. But this calculation will work nevertheless. So we have English units. Our boundary is simply supported. And our length is going to be 18. Then we'll have 16 inches. And the decimal equivalent of 1/16 of an inch. Be aluminum. So we have our library properties there. Our library mass density. We could add non-structural mass, but in this case we're not. Response is going to be, we want the response right in the middle of that plate. Okay, our amplification factor. We're doing 3% damping, which is a somewhat realistic damping. Let's go up to 5,000 hertz. Okay, so just sort of glance over, and eventually we're going to be saving our von Mises stress, power transmissibility. So I'm going to type in VM _stress _trans. I'm going to do a Control-C, Control-V. We're going to need this in a moment or two. But we still need to calculate the modal response of our plate. So let's calculate its modal response and also its transmissibility. So a bunch of plots pop up, and this sort of looks like a kind of like a turtle shell, although obviously if we had a top-looking bottom view of a turtle shell, we would see more of an oval shape at the base. But you get the idea here. This is our fundamental mode of our given plate with its simply supported boundary conditions. and the natural frequency is about 42 hertz. And it's going to turn out that this fundamental mode is going to be the one that's most readily excited, and it's going to contribute to, it's going to have the highest contribution of all the modes to the fatigue damage. And again, we're going to take our fatigue damage right at the center of this plate, where we are also going to apply a stress concentration factor of 3.0. So here is our plate there, fundamental mode. We have a number of plots here, and a couple of these I'm just going to ignore for now. Let's take a look at the displacement frequency response function, and this is at the center of the plate. So this is displacement divided by pressure, so inches per psi, versus frequency in hertz. And here's our 42 hertz mode. So if we had, say, a broadband acoustic input, we would expect that this fundamental mode is the one that's going to be most excited and will dominate the response. And that would be especially true if we had a white noise input. It is possible if our input were strictly limited to, say, a narrow band at higher frequencies, then these higher modes would be the ones most excited. But typically, in many cases, our acoustic pressure field will be broadband, and it will be typically this first mode that is the most excited. So this is the displacement frequency response. And actually, there are some other modes here that are not making an appearance. I'll talk about those momentarily. Now here is the von Mises stress response. So this is the von Mises stress response at the center of the plate. So this is an interesting unit here, or dimension. We have stress over pressure. Now stress and pressure are really two different things, but they're two different parameters that have the same unit, psi. So it's psi divided by psi. Stress is what's going on with the internal material of the plate, and pressure is due to the external acoustic pressure field, which is the applied pressure. Again, we have and this is versus frequency in hertz. Again, we have the fundamental mode at 42 hertz is dominating the stress frequency response. But there are some also contributing effects from higher modes as well. So we see the higher mode contributions there as well. So if we just want to do a simplified analysis, we would only include the first mode. We could include additional modes, but we get a diminishing returns effect as we include those. But all things considered, it is a wise choice to include the higher modes as well. So we've taken a look. Oh, we need to take a look at one other thing. So we have this in our command window here. We have a whole series of our modes. So you can see the modal frequency, and then the M and N indices refer to the mode shape. We have participation factors and effective modal mass ratios, and I've got papers on my blog. You can read more about how those parameters are calculated. But the important thing to know is that the higher the participation factor and the higher the effective modal mass ratio, the more excitable that mode is. So it's the fundamental mode that is the most excitable. Now you'll see the second, third, and fourth modes are not going to be excited at all, and that has to do with the fact that we have a uniformly distributed external pressure field. So if we have a mode, say divide the plate into two halves, either along the width or length, and if those two halves are vibrating out of phase with one another, that mode cannot be excited with a uniform pressure field. Okay, so for most of the modes cannot be excited with a uniform pressure field. But there are some higher modes that can, although you can see from their participation factors that these higher modes that are excitable are less excitable than is the fundamental mode. Okay, so let's see. So the next thing we're going to do is actually save this von Mises stress transmissibility, and this will be for the center of the plate. This does not yet have the stress concentration factor applied. So let's save that. Now once we've saved that, we can calculate the response PSD. Because all we've done here is, well, we've done the modal analysis, we've applied damping, and we've got these transmissibility functions. Well, let's actually calculate what the response PSD is going to be. We click this button. So the input PSD must have two columns, frequency in hertz and PSD in units square per hertz. And the power transmissibility must have two columns, frequency in hertz and transmissibility in units squared divided by units squared. So for this case here, we've already saved the von Mises stress as a power transmissibility, so that means we're good to go. So the power transmissibility is from von Mises stress. Our input PSD, which is from the 737 data, is aft underscore PSD. The y-axis label here will be, this will be for the response PSD, so let's make this the stress in PSI squared per hertz. We'll go from 10 to 5,000. Are we going to save this array? We're going to save it to stress PSD. Okay, but before we can save that, we have to do the calculation, so let's do the calculation. Okay, now this does not yet have the stress concentration factor applied, but this is the von Mises response PSD, stress response PSD. It's at the center of the plate. The overall level is going to be 263.1 RMS overall. That's PSI RMS. So we have the stress PSI squared per hertz versus frequency in hertz. And the overall level is dominated by the first mode. And actually, just to make this, what we can do just to tidy up that title a little bit is let's put in that that's a PSI RMS. So let's replot. Okay, that's a little more proper. So 263.1 PSI RMS, again, von Mises stress at the center of the plate. We have not yet applied the stress concentration factor. We can park this off to the second monitor, which is, you cannot see that. Let's go to fatigue toolbox now. So fatigue toolbox, in this case we're going to have a PSD input, and we're going to calculate the damage for a stress response PSD. That's going to be choice number 2, miner's damage for stress PSD. So we've run this function before. This script calculates the palm grid miner cumulative fatigue damage from a stress PSD via a number of methods. The input PSD must have two columns, frequency in hertz and stress in units square per hertz. So in this case we have PSI, we have stress underscore PSD. Our duration now, the duration we're just going to have that at 1 second, because what we're really just interested in is what is the fatigue rate. And that'll become clear in a minute or so. Our stress concentration factor is 3, so we've not already applied it, so now's our chance to apply that. We have the aluminum material here with its default parameters. Let's calculate the miner's rule. Okay, so what I'm finding now is a pesky error message, which means I did not yet save that stress PSD like I said I would. Okay, so let's see. I needed to click the save button. Okay, now I've saved the stress PSD. I do not mind making mistakes because, you know, who knows, you might make the same mistake sometime. Okay, we're done with this one. Let's see. Okay, here we are back again. Now we have this stress PSD is now called in to our MATLAB workspace. Now let's calculate. So here's our stress PSD again. It pops back up in this function. But what we're really interested in is the results interested in the command window. And this is our fatigue damage. So let's go to our command window here. There's a bunch of esoteric parameters, but mostly I want to concentrate on these different methods here. And there's two columns. I want you to see the cumulative fatigue. This row here, that is the cumulative fatigue damage for 1 second. And then the damage rate is numerically equal because the damage rate is 1 per second, but we only have a 1 second duration anyways. So we could either take the value from the first column or the second column, doesn't matter, it all comes out the same. Although I did include additional decimal places in the damage rate. But now another thing you might notice, and please don't get too disheartened by this, is that there is some spread in these different types of frequency domain methods. And we're not going to worry too much about the spread. You have to realize we're dealing with a fatigue exponent of 9.25, and that actually makes quite a bit of difference as to how these different damage metrics come out. And the approach I have taken is I consider 6 of these to be the best of the methods, and then I just do a meta statistic where I take the average of what I consider to be the 6 best methods. So we're just going to go ahead and take 9.236 e to the minus 15, and that is the miner's fatigue damage that happens over a 1 second duration. So over a 1 second duration, that's what we get. Let's go back to our slides here, and you'll see how I've put these numbers together. So, but by the way, when you see these different dialogues here in the PowerPoint slides, the pathways are given here as to how to get to those these different dialogue functions, or these different functions with their dialogue screens. Okay, so here was the sound pressure level from the Boeing 737. Here was the corresponding PSD. We've taken a look at this already. Here's where we did the rectangular plate calculation to do the modal analysis and to also get the von Mises stress power transmissibility. So that's just a review, and of course I'd like you to do this for homework. And when you're doing this for homework, you're also welcome to change some of these parameters. If you want to look at the response at different locations or try different materials, you know, that's all well and good. That would be good for you. And we took a look at the rectangular plate natural frequencies, the indices there for the mode shapes, and then the participation factors and effective modal mass ratios. If we took enough modes and we took a summation of these EMM values, eventually the summation would converge to 1. And here was our kind of looks like a turtle shell fundamental mode, where most of our stress and fatigue damage is due to the response of this first mode. We took a look at the stress frequency response function at the center of the plate. This does not yet have the stress concentration factor applied. Then we did this multiplication where we took our forcing function, which is from the 737 data, that power spectral density. We multiplied it against the power transmissibility in order to get our response PSD. And our response PSD has stress units, psi squared per hertz. So here is our stress response here, 263.5 psi RMS overall. That's at the center of the plate, and this is the von Mises stress. Then we went to our fatigue toolbox here, and we're doing this choice for the PSD input, where we have miner's damage for a stress PSD. So we then did our polygram miner cumulative fatigue damage from the stress PSD. And at this point, we finally did apply our stress concentration factor of 3 with our aluminum material there. And we came out with a damage rate equal to 9.53 e to the minus 15. So this is the cumulative damage, simply supported rectangular plate, center, stress concentration factor equals to 3. We have our margin here, so what I've done is 0 dB corresponds to the direct data we took from the 737 for our altitude Mach number. Then you see the PSI RMS stress. This is without the stress concentration factor. Then we have our damage rate, which does include the stress concentration factor. So for this case, for our 0 dB margin, what would be the time till failure? So let's set our failure equal to R is equal to 0.7. So our time to failure would be some almost, you can almost say, arbitrarily long number of days that will far exceed the days that any of us are upon this earth. So you might say, well, no problem. There's no problem, right? Well, that's good, because if this plate were actually a panel on that 737 fuselage, we do not want failure to occur. We want plenty of safety margin. Well, what if we bumped up the margin to 6 dB? So each time we go up by a 6 dB increment, that's going to double the RMS stress. But the damage rate does not double. It goes up by 2 to the power of 9.25. And 9.25 is the fatigue exponent for aluminum. So you can see what's happening to our time to failure in terms of days. These numbers are also going up by 2 raised to the power of 9.25. Then there's a margin of 12 dB and a margin of 18 dB. So at an 18 dB margin, then failure would occur after 3.77 days. So let's see, what was our overall sound pressure level? So our overall sound pressure level for the 737 was 135 dB. So if we go up in terms of an 18 dB increase, then that would be 153 dB. So if we have that level but raised to 153 dB, then our failure occurs in 3.77 days, which would be a bad thing for an aircraft. Now for fuselage, the fuselage is never going to get up to 153 dB. But if this were some plate or panel adjacent to the engine, then yes, or on the engine, maybe the engine housing, for example, then yes, the level would get up to, would in all likelihood get up to 150 dB or so. So that's just something to keep in mind. Now, really, I've oversimplified this because all we're doing now is the acoustic fatigue due to the, we'll call it to the attached flow or turbulent boundary layer, whatever it might be, at that Mach number, at that altitude, and at that aft fuselage location. But aircraft are a lot more complicated, especially the fuselage, because the fuselage, okay, let's go to this slide here. Aircraft fuselages undergo repetitive cycle of differential pressure with each flight. The difference between the cabin and the external ambient pressure is about 6 or 7 psi at an altitude of 36,000 feet. Note that the cabin pressure at high altitudes is maintained at about 75% of the sea level pressure, which corresponds to the air pressure at about 8,000 feet. And this is done or maintained by pumping air into the cabin. And as you might well imagine, there's some variation to those numbers depending on the aircraft model and maybe some other factors as well. But this pressurization, this repetitive pressurization cycling, that also causes fatigue. And that may in fact be a greater fatigue source than even this acoustic fatigue. I'm not sure. It's something that would need to be checked. So if we are going to, in earnest, do a fatigue calculation for a fuselage panel, then we need to account for pressurization cycles along with vibrations, acoustics, Then there's these other things as well, corrosion. What about salt fog? What about humidity? What about thermal cycling? So all these different factors can cause fatigue cracks to form and propagate. So I want to be very upfront and honest about that. What I have shown you today is a way to do just one part of this calculation. And here's what can happen in an extreme case. And many of you are probably familiar with this, or some of you. Aloha Airlines Flight 243, and that was between Hilo and Honolulu in Hawaii, suffered extensive damage after an explosive decompression in flight, and that occurred on April the 28th, 1988. And this was a Boeing 737-297 aircraft. It was able to land safely at the Kahului Airport on Maui. Sadly, there was a fatality. There was a flight attendant who was basically sucked out of the aircraft and swept overboard. And what was found afterwards was fatigue cracks had occurred due to the disbanding of cold-bonded lap joints and hot-bonded tear joints in the fuselage panels. And that caused the failure to occur. So the rivets were overstressed. That was another thing that happened. As sort of a chain reaction. A large number of small cracks in the fuselage may have joined together to form a large crack. So I would say, just somewhat at a distance here, is that this fatigue failure was probably due to a number of things. It was due to the repetitive pressurization cycles that this aircraft had undergone. It was partially due to the acoustic environment as well. And when I say acoustic environment, we sort of use that term kind of loosely. The more proper term we should use is the applied flow field. So it was really an applied flow field environment. But just sort of out of laziness or simplicity, we often refer to that flow field environment as being a sound pressure level. But more properly, what we've done today is taken a look at a external flow pressure level rather than a sound pressure level. But you get the idea. Now this aircraft operating in Hawaii area would have been subjected to the salt fog and humidity type of environments that are typical for the coastal areas. So that could have also been a contributing factor to this failure. So I guess that's about all for today. Again, this was just a really simplified introduction. And what we're going to be doing in future units is we'll further develop this, and we're going to be a little bit more, go into details more. We need to take a look at the cases where the pressure field is not uniformly distributed. What if there's spatial variation to that pressure field? What if there's the phase angle variation? There are different effects that can occur, especially for larger plates and panels due to the external flow conditions. There's different types of acoustic fields. There's diffuse acoustic fields, there's progressive waves, there's oblique incidence, and all these terms we have yet to study. So hopefully in future webinars we'll take a look at other flow field conditions and acoustic conditions as well. But if the plate or panel is small enough, it's probably a good assumption and conservative to assume that plate is being acted upon by a uniform pressure field. That's all for today, and we'll see you next week. So thank you, and goodbye for now.